Okay, so in these slides, we're going to look at using the Fourier series to find the frequency content of a signal. So remember, our application here is the sampling theorem. So we're trying to find what the maximum frequency is in our signal so that we can sample at least twice as fast as that maximum frequency. So the Fourier series is an algorithm that lets you write any function of time, any analytic function of time, in a given range, t between 0 and capital T. You can write that function as an infinite series of sines and cosines. So here f of t can be anything, any kind of f of t can be rewritten as a sum of a0 plus a1 cosine omega naught t, a2 cosine 2 omega naught t, a3 cosine 3 omega naught 3. You can see the pattern there. And this goes on to infinity. And then there are sine terms with b1 sine omega naught t, b2 sine 2 omega naught t, and so forth all the way up to infinity. So if we write them as sines and cosines, the frequency content is really easy to see because we have a frequency right here. The fundamental frequency is set by our period, capital T. So when A and B are small enough, then we can find the frequency where that happens and find the maximum frequency in the signal. So let's look at finding these coefficients. So the A and B coefficients have equations here. If you have your given function of time, you have to integrate it. So A naught is just the integral of the function between 0 and capital T divided by capital T. For the an and bn terms, the a1, a2, a3, and b1, b2, b3, etc., we have the function times either a cosine or a sine term that we have to integrate over the same interval. So it's just some integral math that you have to do. It can be a little time consuming, but it's not impossible. If you're solving for a few terms, like if the homework problem says find the first 3 terms of the Fourier series, you might just use your calculator's numerical integration function. But in general, we want to leave n so we can find an, and so we have to do them analytically or with symbolic integration. Integration by parts is usually the easiest way to solve these integrals by hand. If you remember integration by parts, u dv, that integral is uv minus the integral of v du. Usually you choose u to be the function of time and dv to be the sine or cosine function. So here's an example of the Fourier series. So our initial function is f of t. It's t over 2. And the interval is between 0 and 10 seconds. So in red here, we see it's a ramp function. So the first thing we want to find is that omega naught, the fundamental frequency, the low frequency. And it's just 2 pi over capital T, so pi over 5, radians per second. Then we have to find the coefficients. So a naught is the integral here, and it comes out to 5/2. An is the integral here, and it turns out, because of the periodic nature of cosine, all the an's are 0. The last coefficient we have to find is the b terms. The equation for bn, the nth term, is given here. Plugged into our function, we have f of t sine n omega naught t dt. And if you take this and integrate it by parts, you'll find that bn as a function of n is -5 over pi n. So now we can write the function t over 2 as an infinite series of sines and cosines so that we can find the frequency content. If you want to see the integration by parts, I'll put this as a PDF that you can look at a little clearer. but this shows how to do it numerically, like your calculator probably can do. Integrating by parts is on these next few lines, and it goes through all the math all the way down to this part. So putting it together, we started with this function t over 2, and now we can write that as this infinite series of sine terms plus 5/2. So that's really interesting. How do we use that to find the maximum frequency? Here's frequency as a function of n. In theory, the frequency goes to infinity because this is an infinite series. So there is no perfect answer to this. So we have to decide how many terms is a good enough approximation to our original series. So a good way to think about it is the amplitude on these sine waves is the b term, so -5 over pi n. When that amplitude is close to 0, then the whole term is close to 0. So if you can find an n where this 5 over pi n is approximately 0, the frequency that corresponds to that is over here, n times pi over 5. So I should leave that t off. N times pi over 5 radians per second. So you need to convert that to hertz. So this is just showing another way to see how many terms you need to keep. So another way is to include terms until it looks pretty good. So here is our original function, t over 2 in red, and here is the Fourier series with just one term plus the constant, so n equals 1. And it's a sine wave, and it's actually not too far off here in the middle, but it can't get the corners. The corners are hard to do with sine waves. With two terms, we have two sine terms now. You can see it's a little bit closer. The maximum frequency with two terms is 0.2 hertz, so still pretty low FM. And the other thing you can see is that the formula is guaranteed to work between 0 and 10 seconds. Outside of that, the Fourier series algorithm doesn't say anything, and so it turns out that the function's periodic, so it's going to repeat from 10 on and before 10. So you'll see this repetition as we go along. So here's three terms. It's getting closer, still has trouble on the corners. Four terms, a little bit better. Here's 10 terms, so now our FM is 1 hertz, which is still a pretty low frequency. And it's very close in the middle, still has trouble with these corners. 50 terms, we get right in there in the middle, a little bit of strangeness on the corners, but not too bad. That would be a 5 hertz FM. And if we jump all the way to 1,000 terms, as an FM of 100 hertz, it's really, really good. Still, you can see a little bit on the corners, but otherwise very, very nice. So that's one way to find FM, is just look at it. So from eyeballing these plots, your eye is a very accurate judge of things like plots, so it's a good tool to use. 50 terms we said was okay. That's a 5 hertz FM. 1,000 terms, definitely okay, and that was 100 hertz. So if your system can sample at least 200 hertz, which most systems can, you'll be fine. Even if you can only have an FM of 5 hertz, that would be a sample rate of 10 hertz, and that should be really easy to do. So the nicest way to think about this is to plot the amplitude of the B term as a function of the frequency of the sine wave, and look for where that goes to 0. So wherever this graph goes to 0, that frequency is FM. It doesn't really go to 0, it's 0 to our engineering precision. So looking at this graph, 5 hertz is down here, and it's definitely not 0, but it is small. At 40 hertz, we're looking very small, and remember we said 100 hertz was definitely good, and it's right there on the line to the precision of this graph. So this is the best convincing way to decide what FM is using frequency analysis. So it's worth repeating that this line doesn't really go to 0. It approaches 0. So we're making a judgment on what 0 to however many significant figures we're interested in is. And the frequency where that happens is what we're interested in for FM. Later, we're going to use the fact that in a data acquisition system, your analog to digital converter might not be able to have to measure very small voltages. So if it's 0 to the precision of the analog to digital converter, then it's 0 for all practical purposes. So where this goes through 0 to the resolution of our measurement system is another approach, and we'll use that later in this class. So that should give you an idea of how to do the Fourier series and how to use the Fourier series to find FM for the sampling theorem.